Right. So let's begin this class. As I said, today will be the last part of this assembly theory. So we've talked about a normal compute instruction. We talk about loop. We talk about if else, right? So the next thing we need to cover, essentially, what's left? Anyone want to guess what is left here? To make sure that, hey, I can run a program. What is the first thing I need to do when I type enter? When I run a program, it go into the main function, right? Which basically means that I need to somehow support function calls, right? And to support a function call, basically these are the general guideline. First of all, when you have a function called something like this, right? I have a function called P and Q, right? And let's say P calls Q over here. So P calls Q, X go into the input over here, and then you keep running. And when you return this array, right? And somehow you would like to hope that, hey, somehow this would work, right? Somehow I would have a correct result. But then, if you look at the assembly code, nothing resembles your function. It's just a straight line, right? Straight line instruction. Do this, followed by this, followed by this, followed by this. If this is true, go back to this, and then keep doing everything. A function is also another straight line code, or not. But basically, it's another block of code as well. But then you need to make sure that you can jump to the correct point, and then also making sure that you can pass data around. So first of all, the first thing I want to differentiate is what is a control and what is data. Control, when we refer to control, is basically how we control, as definition, how I can control everything, how I can control the flow of the program. Do I go into this function, and when it's done, where do I come back to, right? Over here, once I finish y equal q of x, can someone tell me what is the line of code I can go back to, or I should go back to? So what's the next line of code that I should run after I finish y equal q of x? Like I finish the entire function q. Print y. Yep, exactly. Basically, that's the next line, essentially, right? But somehow, if you look at your assembly code, right, recall the program counter. The program counter points to the current instruction, which means that once you're in the function q, right? So let's say this is p, this is q, right? And this is the line that you're jumping, right? So basically, this jump to here, you keep running, blah, 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 blah. Here, this is where the program counter is at the end of q. And somehow it would have to magically point to the next line over here, right? Somehow you need to make that happen. Somehow in the assembly code, right? You need to write an assembly code that this happen. So this is the control. It controls how you keep track of these are the function calls. And when they are done, run the next line right here. Don't run random code, run this line right here. The next thing you need to make sure you pass into the function is obviously data, right? Here, if you have the input x, right? So data from x is passed into this variable I, right? Basically, somehow this new variable I has to take whatever value x is, right? So these is basically the process of you also have to pass in the data. Then at the end of the day, when you return, right, you also need to return the data back. How would you return that? In x86, the way you return it, it actually has certain assumption. One register would be determined as a return value. Whatever value goes in there is my return value. And it's only one register. That's why when you write a C code, you cannot return an array. So this return V of T, right, is one value inside V, right? You can't return an entire array unless you give out the pointer. That is exactly why, because it's only tied to one single register. So you only can return one single thing. And then you need to make sure you manage memory, right? Let's say inside a function you call malloc. Upon return, how does that memory works? What about this thing when you have int t equals 3 multiplied by I, right? When you return that function, t would be unknown. No one can access t anymore. So you need to also figure out how to manage the memory. And at the end of the day, right? At the end of the day, think of it as these are rules that are governed by whatever that human designed the ISA. For example, in Intel x86, whoever come up with that x86 architecture and that ISA manual, they would actually write a really detailed document on this is how you pass a function. RAX, for example, is used as a return value. And they'll specifically say that if you want to return from a function call, put that in RAX. So that's why we will say this, right? When you design a machine, it's basically this become a book that say, okay, this is how you call a function. At the end of the day, human design the computer. So we design how this works. And this is a normal convention, basically. As I point out earlier, right? The first thing is to pass down control, and as I highlight here, there are generally only two things you need to care about here. When you begin the function, right? When you call q of x, you need to make sure the program counter point to this line. And then when the function finish, the program counter somehow take this line. That's all. Any questions? It's basically as simple as that. How? We'll talk about how later, but right now, let's think about the high level idea. You want your program counter to take the correct line of code. Where is that line of code? It is at certain address in DRAM, so it just need to take the correct memory location. To pass the data, what we mean is, as I said, x has to become I, v of t will be written into y when you finish this function, right? And that's all. Memory management here is when you have v10, how do you allocate, right? How do you allocate this? And this, as I said, it would have a rule book, right? That the ISA designer would declare that this is how you would allocate memory. And this can change from one architecture to another architecture. This is hardware level optimization on how you would manage this allocation. This is basically my own research. Like basically, this is something that I would have to decide and put that in a rule book for all the programmers, right? So I am the computer architecture researcher. So I would actually make this thing, and somehow everyone else has to follow my rules. And hopefully my rule is good. Hopefully my rule is easy to program, easy to use, fast, and correct. Right? So this is my job to make sure those goals are satisfied when I design a piece of hardware. So by this point, many of you probably realize one of the most common assembly code or the ISA is x86, right? It's from Intel processor, AMD processor. Every single piece of desktop, laptops, except I guess Chromebook, some of them might use ARM. They use x86. I guess except for I have heard that MacBook and MacBook Pro will switch to ARM architecture in the near future. So that might change a little bit, but now one of the more common ISA is x86. And the way they manage function calls is there is this stack, right? So anyone here still have question about stack, or what do they mean when I said, hey, I am managing everything in a stack? Here is how it looks. A stack is a region of DRAM. Let's say you buy that DRAM and put that in this 1D dimensional from address 0 to address at 16 gigabytes, right? A stack is a location somewhere in there. It's a flat 1D space, right? And it behaves like a stack. This is, let's say this is the region in DRAM. So this is your DRAM, right? A stack would have the bottom part and the top part. And if you recall 2 lectures ago where we point out the register, right? And we said this RSP, this stack pointer, has special meaning. Basically, the stack pointer point to the top of the stack always. So don't modify that register randomly. You can modify it, but you need to know what you're doing. Basically, it would maintain these stack in the OS, right? What would happen if I push the stack? Does the bottom grow or does the top grow? So do I grow my stack this way or do I grow my stack that way? All right, what is a stack? It's first in, last out, yeah. So actually it's first in, last out. FIFO is a queue. First in, first out is a queue. A stack is first in, last out. So it grows from the stack top. So it actually go down here, right? The top part of my stack, if I put something in, it grow up. But because I flip this, it goes down. Basically, I flip the figure, so it's actually go like going downward from here. So if you look at DRAM, some part would be this stack, some of these would be your code, right? Your own code. And some of them would also contain another region of memory called the heap, right? But let's look at the stack and what do they mean? It's basically it's a region of memory that is managed. And the way you manage it is through the assembly code, right? It goes toward lower address. So if you put in your address, whenever you put something into the stack, push would make the RSP. Push, would it decrement or increment RSP? If I say grow toward lower addresses, does it increment or decrement when I push? All right. Grow toward lower address means that the new item would have lower address. So if RSP point to the top, the address for the top, if I put in new items and the new items has lower address, do I decrement my RSP or do I increment my RSP? Lou, are you here? Or you can guess so I can tell the answer. Okay, so again, please, my question is whenever, okay, yeah, that's fine. That's okay. Basically, whenever we add a new item, right, we as a human would be like, okay, we would increment the address, right? But I said, whenever I have a new item, it go toward the lower address, which means that the new item should take the address that are in the lower. So let's say this is 0x00. Okay, 004, for example. if my item is one byte, right? Let's assume it's 1 byte, and I push. Now RSP would point to the top, like the new top, which would be at 0x003. So I would decrement, right? I decrement the RSP when I add a new thing in. When I pop, which means I take something out, I would then increment my RSP. RSP acts like that top pointer when you implement the stack in C, or it acts like the top variable when you need to increment or decrement the stack in Python or Java, right? And as I said, this is basically contain the top elements. So this is what happened when you push the source in. I don't know why the ink remains here, so let me remove that. Erase. It doesn't even allow me to erase. Okay. I said interest. Pop interest. All right. So you still have a question. So basically the question that asked privately is why does pop decrease? It's actually not, it's increase. When you pop, you increase the value. When you push, you decrease the value because the stack go toward the lower address. And here, so let me show some animation. So hopefully this is a little bit better. So when you push source, what happened is basically the operand. So this can be, say, for example, R9, right? R9 register name. What the computer would do is to go grab that data. Whatever is in R9, right? That value would go into this slot, the new slot that were there. And my question, you see RSP is going down by 8, right? Can someone guess why is it going down by 8 and not 1? If it's going down by 1, it means we are pushing our value is 1 byte. That's correct, right? But in a 64-bit machine, how big is my data? A 64-bit machine, yep, is 64 divided by 8, which means that I would then decrement it by 8 because my register is 8 bytes long. Basically, val here take 8 bytes because every single register is 8 bytes. So you decrement RSP by 8. Any questions about decrement by 8? Why is that the case? And not 1. So basically, because val take 8 bytes, it's that big, right? So you need to go down by 8. So how about pop? So basically, this is the update. RSP would be right here. Yeah, so every time you push so you don't have to manually do this when you call this function. So let's say you use this assembly code push kill source in your assembly file. Your RSP would be decremented by default. It would do that as well. So RSP will still correctly point at the top of the stack. But if you print out the value of RSP, you then notice that now it's going down by 8. So yeah, that's a great question. Basically, you as a programmer doesn't have to do it if you call push, that would go down automatically, but you need to know that now the RSP would change whenever you push. So pop is kind of the same. Basically, pop would pop things out from your stack, and now you notice RSP rev up, right? So it get increment by 8. And then the value here would then sorry. The value would then get stored in whatever register here in the destination. One thing that I want you to notice here is when you pop, even though the value gets stored in destination, this value that is already on your memory, nothing changed. The old value is still there. It's just that you increase the stack and now some register already took that value. So that's one quick thing where you might have noticed when you call malloc, right? When you call malloc for the first time, you see some junk that are not zero. Why is that the case? Those are junk data that someone else has used and free. When you free, it doesn't mean that someone would go scrub out all the data and make it zero. It doesn't really happen that way. Why? Why bother deleting, right? This is actually this same concept is almost similar in how you store files. So how many of you know that when you write something to your computer, when you save a file and you delete it, even though you delete it from the recycle bin, the data is still on your hard drive? How many of you know that? Essentially, the operation is go and read, basically write everything and scrub everything. That takes too long. So the file system that are written by the programmer will say, okay, just mark that location as free. Someone can write over that, but the data will still remain there. So this is kind of the same concept in DRAM, in the main memory. Why bother trying to write something to zero if you don't need it? Just free and keep the data there because no one would have access to it anyway. Right. Any question or push and pop? Because now we'll talk about when we actually do the function calls. So we covered the stack structure. We will now talk about the calling, basically the convention. What do you do when you call a function? And it involves 3 steps. Passing the control, which I would summarize it to, okay, how do I manage my program counter? Followed by how to pass the data and how to manage the local data. So we'll use these code example. This is the C part. This is the assembly counterpart. So it's the assembly of this. This is the assembly of this. I want to point that out first to make sure that it's a lot of things in one slide. I want to make sure I categorize each of the box. There's a C box. The assembly box of the same color represent the assembly code of that function. So what does this function do? Can someone explain what does this function do from the C code? Yep, take A and B and return the multiplication of A and B. Okay, and that's it. And then you also return. So these function call the mult2 function, multiply 2 numbers. And if you look at the assembly code, right, there are a few things that you might have noticed. RETQ, every time you've been reading assembly code at the end of a function, there's this particular function, RETQ. Can someone guess what RETQ do? Return, exactly. So there's also a function called callQ, right? CallQ. What does callQ do? CallQ basically call a function. Where is that function? Here, 400550. So you notice that this is the beginning of my function. These 40050 would map to this box. It called this function, which is stored at address 400550. Okay. My question, right? My question is, okay, let's assume I'll use a different ink color. So hopefully this is a little bit more clear. Right. So when I'm at this line, my PC value is program counter is 400544, right? What is the next PC value that I should take? Is it 400549 or is it 400550? Yep. Somehow it would then take 400550, right? And then keep going for 553, right? This line, and then this line, and then return. When I return, what should be the value of my PC? From here, right? From here, what's the next line? Yep, 400. So it should go to 400553, right? And then 400557, and then go back to 400549. Right, so it from here you go back to this line. Basically 400550, 400553, 400557. When you hit return, 400549. My question is, how can I magically know that I have to go back to 400549? Yeah, return, right? So when you see the return, something happened. So can I do something with the stack? When I have call queue and return queue. Right, so I know that somehow I will have this magical data structure called a stack, right? So one thing I can do, yes, push and pop. So when you have call queue, do you push or do you pop? Exactly, yeah. So that is the correct answer. You need to save this, right? You need to save either 544 or 549 depending on your hardware description, but over here, let's assume that we save what is the next instruction, right? So you put 400549 on the stack. And now RSP is here. Then you are in this function, right? Because you have that information already, blah, 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 blah. That's what happens when you do call queue. So what happened when you do return? Okay, again, please, yeah, sure. Basically, when you face this call queue function, two things happen. I put this as my PC value, right? That's my next instruction. But if I do that, I lose the fact that I need to come back here to 549. To make sure I don't lose this location, what I can do is right before you jump to 400550, right before you jump here, you can put the next instruction on my stack. This particular address get pushed into the stack when you call queue. Whenever a call queue happen, you can push the PC value that you're supposed to run next into my stack. Just so that I can say where do I return when I need to come back here, right? Then when you have a return queue right at that instruction, what do? I pop my stack, right? RSP would then point here. This value would then get replaced the PC. Now you have 549. Any question? Basically, when you call a function, push the value that you're supposed to return to on the stack, so that when you have return here, the return assembly code, right? You know exactly where to return. And here's the more like a procedure in the explanation in wording format. Essentially, you can use the stack to support this. Whenever you call something, you push the return address to the stack, then jump to that level, jump to that new function. And then when you see the return function, you pop the address from the stack, jump back to the old function. Any questions about this? Otherwise, I'm gonna go through this example. This is my function pointer. Basically program counter. I refuse to use the word instruction pointer. That is a really old word. Let me use an architecture term, which is program counter. It's the same thing. Instruction pointer, program counter is the same thing. So here, as an example, you have the call queue function, right? Followed by a return queue function here. So when I do call queue, right? Call queue, this is what happened. Notice, so this is my stack, right? And I know my animation doesn't carry over my marking, but when I go to the next slide, when I call my function, what would get stored here at 0x118? Actually, first question, do you know why it's 0x118 and not 0x, for example, I don't know, 112? It's hexadecimal number, so when you subtract 120 by 8, it's 118. It's not 112. So just be careful. Whenever you see 0x, this is the hex number. So if you subtract 8 to 120, it's 118. Okay, so is that clear? Basically, 120 minus 8 in hexadecimal, that's 118. So if you subtract 118 by 8, you get 110. It's just this is a base 16 number, not a decimal number. This is hexadecimal. That's why it starts with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Right. So if you subtract 120 by 1, you get 1 F. Then by 2, you get 1 E, 1 D, 1 C until 118. That's when you subtract by 8. So what do I put on that box? When I do call Q, what should be pushed on that box that I just draw? Yep, exactly. C44059. And hopefully when I go to the next slide, that's exactly what happened. So what do I do with RSP? This should be updated to what value? 18, right? Because we subtract that by 8. And when I call the function, what do I update this with? What is the function address? Yep, correct. 400, sorry. 400550. Right. So I hope when I go to the next slide, these are the exactly 3 things that happen. So let's check. Okay, great. All right. So we are at the correct steps here. Now we call a function. We correctly manage the stack. We correctly manage the stack pointer, right? We correctly manage this part. We correctly manage this part. We correctly manage this part. Okay. What would be the value of my program counter at this line? What is my RIP? 400557, right? So let's say we are at that line. Let's say we are at that line. When we want to come back, what happened? When we want to come back to the calling function, right? So we'll call this. Yep, exactly. You pop this. This thing get popped into this, right? You then decrement this to this. Basically, you pop the stack, write whatever value you see into there, and then you increment RSP because you already popped the stack. It's just exactly what happened. Now you see how we can call a function and somehow can come back to the point we're calling, right? Any questions about this process? Any questions before we move on to how to manage data we're passing in? Yeah. Okay, I love that comment. So one of your friends said, thanks to high level programming, this is painful. Okay, so why is that 120? When you pop the stack, right? When you pop the stack, you basically need to update my stack pointer. So this was the old RSP, right? And because that element is gone, that you already used that up, so you need to increment it. So my new RSP would point to 0x120. How do you do that? Add 8, right? So 0x118 plus 8 equals 0x120. The hexadecimal number. Make sure you are aware this is hexadecimal number. So that's why it's not 0x126 and it's 0x120, right? Any questions? Basically, if you have a question about how to add hexadecimal number, you need coffee. I think that's probably the only solution here. But yeah, so I think it's that you're tired. Okay, so that's it for calling a function. And yeah, again, I love the comment that said, thanks to the high level programming, this is painful, right? Even in C, you don't have to do this. And I agree. I think I said that way back in the beginning of this class, right? About the level of abstraction. And at the end of the day, even me, I would cry in a corner if I need to hack assembly code, and I still hold true to that word. I don't want to do this, but the thing is, it's good to understand these steps, because sometimes, sadly, you have to do this. Especially if you run into some weird errors and you try to debug your code and you need to like go through GDB, right? When it spits out some weird error code, those actually have meanings. A lot of time it has to do with this addresses, the return function, and sometimes things are wrong, right? So this can happen. So let's go to the next part of this. Basically, now you finish passing the control. Let's make sure you know how to put in the input data to my function, right? Because otherwise my function call becomes pretty useless. I can call a function, but I cannot pass anything as an input to my function, right? So here is the data management part about my function calls, right? You have the arguments that you are passing in. And notice that it starts with argument 7. Does someone want to guess why? So let's say I do int add these, right? And then int a, int b, int c, blah, 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 to int c. So there are 26 total numbers that I want to add. My input has 26 items. What happened in here? What happened in here is in x86, this is specifically to x86, the Intel processor and AMD processor. This might be different in ARM processor. But there are certain registers that would take that the processor would assume that that's my input arguments. So A, B, C, D, E, F, G, H, I, J, blah, 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 C would go like this. Basically, the first 6 arguments of your function input will be stored in these register. If you need more than 6, use the stack. Use the stack similar to how you use it as to store return function. This is return value. So at the end of your function calls, you need to make sure whatever value you want to return is stored in RAX. Any questions about this? Basically, this is defined by the ISA. The first 6 arguments would be stored in this register. The 7th, the 8th, the 9th argument will be stored on the stack. The return value at the end of your function call has to be written to RAX because the caller, the function that calls this function, would assume that that's where my return value is. So let me go through an example. Let me show you the entire code. Right. C code again. Assembly. C code. Assembly. These function call this function. Notice how x and y are the inputs, right? X and y are the inputs. So if x and y are the inputs, when I want to multiply, which register am I multiplying? So if you go back to the earlier slides, you notice that, okay, these are the two registers that would store the first and the second arguments, right? So what you want to do is multiply RDI with RSI, write the result to RAX, because RAX is the return value, right? This is return value. And because you can't just say multiply RDI, RSI, write it to RAX, it's just the limitation of the Intel processor, you need to first multiply. Before you do the multiply, you then first need to make sure IS would take the value A, and then the multiply would happen by this value. So this instruction is basically RAX equal RSI multiplied by RAX. Why do they decide it this way? Design the processor this way? There are certain benefits and there are certain trade-offs. We'll learn that in the next, basically in the computer architecture class. it comes with like how can you make instruction more impact. My bad, not impact. More compact. The code would be smaller. And there are certain trade-off over here. Is a little bit less programmable. You need two instructions instead of one instructions, right? But at the end of the day, you notice that my input here, X and Y, right, is stored in RDI and RXI. Why is that the case? Because you know that this is X and Y again, right? So this is assumed by whatever called the mount store function. Then you notice at the return, right? Return before you return right here, the correct value of A multiplied by B would be stored in RAX, and that's it. Right? Any questions about passing in and out, like data in and out? Yes, no, yes, no. If you have a question, feel free to ask the question because I feel like I think all of you are a little bit tired here. It's actually as simple as you need to assume what register would take my first argument, second argument, third argument, and you start from there. And before you return, that's RAX. If you look at this, you notice that the first argument would be in RDI followed by RSI, right? Which is exactly as here, right? First argument X would be in RDI, first argument, second argument, right? So let me give you an example. Let's say I call a function called add, right? A, B, and C. Add A, B, and C. How can I get C? What register name would store C based on this? The answer is kind of already on the slides, but if I want to get C, where do I get it from? RDX. RDX, yep, RDX. Basically, that's it. Basically, it's a convention that the processor assume, and you need to somehow follow it. Think of it as a handshake. It's a language that you need to follow. It's a syntax in some sense, right? So if I do I don't know, function name and then X, Y, C, A. What would be X? What would be Y? What would be C? What would be A? So X would be RDI, right? That's the first argument. So in this case, I'll write it here. That's X. That's Y. What is C and A? That would be RDX, right? And then RCX. X, Y, C, and A would go into RDI, RSI, RGX, RCX. When you return this function calls, make sure the result is in RAX. The 7 argument, that's a great question. If you have more than 6, they go into the stack. So this is your stack. So you would push, and keep pushing. There's no name. Basically, you would access it using the stack pointer. Basically, you keep pushing, and then you use the stack pointer to access each of these things. Can someone guess what would be the impact of having the 7 input? How long does it take to access the register here? So both of them are OM1. The problem is accessing the register is on the CPU, right? So accessing RDI, accessing R8, accessing R9, that takes about 0.3 nanosecond or less. It's actually that fast. If you need to access the stack, that's about 40 times or more slower. So having that 7, yeah, it's that bad. Yep. You might be surprised, but yeah, there are things that you can do to make it better. We'll cover that in the next lecture when we talk about the memory hierarchy and how to make sure we can hide this cost. But basically, if you need to go to the stack, it's really slow. That's why a lot of programs. That's why when you use this APIs, libraries, and all those things, sometimes they actually modify the assembly code to make sure you avoid using the stack. Because it's a lot slower than a register. So hopefully you have that in mind a little bit when you write a program that, hey, if you have a function with lots of arguments, that can be slow. Any other questions before you switch? So, because when you represent things in a big O notation, right? Big O notation is basically something that are based on the number of your inputs. So at the end of the day, this is one operation. You move, right? Basically, you accessing by moving something to the register. If it's already on the register, it's all one. Basically, it's one operation. If you need to access something from the stack, you move, right? Basically, then you would do this, right? This is your base. The number here, this is the element, right? And then 8. You move this into your destination. This is how you can access. So this is how you can access the nth element on the stack. And just make sure it's negative here, right? You can just, well, you can pop, but pop modify RSI. So that's dangerous because that might pop into your function calls. Most of the time it's safer to kind of like manually control RSI. So in this case, if you need to put in more than 6 elements, you would then manually, you can push actually, but then when you pop, that value is gone. Right? So you would then just move based on the relative position of where you want to access. Right? Okay. Can we? Yeah, basically. Okay. So let me answer. So there are 2 questions. The first question is a little bit more complicated, so I'm gonna answer that second. The second question is, can we just take a peek? Yeah, that's exactly what we're doing here. Move is basically we're taking a peek on the stack and get that value without changing the content of the stack. We peek onto it. Right? That's how we can put in the input that are more than 6 elements. What is RPX? Why we have to save the pointer first and not use it right away? Okay, so if you go to this code, right? If you go to this code, one thing that happens here is it okay if I clear the screen and redraw because it's really messed up right now. So I need to kind of draw it on the same screen again. So let me erase everything here. You notice that RBX, oops, my bad. Pen. If you look at this function, that is the third input. So you have X, Y, and destination. Destination, what it is, it basically store the value of this, right? Whatever returns you put it in the destination. This is basically what we will cover next in the next part of this lecture. Because if you notice this, somehow this value is important. You don't want to lose it. Right? You don't want to lose this value. So everyone agrees, right? You need to somehow make sure that if my function here need RDX, this would be gone. So the assumption is this: if multiply by 2 use RDX, my old value is gone. So everyone agree with that fact, right? Any question with that? Basically, if somehow I don't know what is in multiply by 2, if I don't know what's in here, so this is a black box. If this is a black box, I can't guarantee anything. I can't guarantee that RDX would not be used. Then I need to make sure I save it. I need to save this old value. That's why you basically need to save this into some buffer, right? These RBX act like a temp, right? The temp variable to make sure that no one can overwrite that, right? That's why you need to save it. Any questions about this? That's a great question. Basically, this is what we're going to cover next, which is how to manage the local data. And okay, my bad. So let me go back to this slide. Manage the local data inside a function. They need register too, right? They need register too. So it means that if we need to use like need RDX here, you need to make sure this is done. Any questions? Basically, that's it. You need to manage the local data by making sure that anything that can potentially be overwrite, back it up. Back it up in some register. You can even back it up on the stack. Okay, again. The first assumption is with X and Y in RDI and RSI, right? Those two things would be used inside the function. But then you can't guarantee that the destination here, that are in RDX, will not be overwritten. Mouth2 might overwrite that by accident, right? So to make it safe, you can back up that data. So if you look at RBX, right? If you look at RBX over here, you'll notice that RBX is not on this list. It's not on this list. So you can use it as a temp variable because it's not being used as a potential register in the arguments. But that's not always the case, right? So when you write the program, make sure that if you need to overwrite some old register value, you can save it in a temp register, or you can save it on the stack. So in this particular instance, you save it on a register that you know that, hey, these functions are not being used. You can then also save it on the stack. That's also a valid procedure. All right. So let's move on. If we still have a question. Yeah, so yes, exactly. It's basically you can call RBX whenever afterward as a temp. In fact, this particular function use RBX instead of RDX at the end, right? And because at the end of the day, assembly is a program, you can modify it as long as you think it's correct, right? These would be what would be the results of the compilation process. So the compiler would do this for you. Why we do not save at RDX? Okay, can you oh I mean okay. Oh, okay. So the question is why don't let me make sure I understand the question correctly. So correct me if I'm wrong. Basically, your question is like, why can't we do this around here, right? Why can't we do this move RDX RBX later? Is that my is that correct in interpretation of your questions? Yes, no. Oh, why do we not store it back? Okay, that's another good question. Basically, because at the end of the day, uh, it just happened to be this particular function doesn't do anything else, so we know that RBX still have that value. So there's no need to add one more instruction. So you can store it back. That's for sure. You can store it back, but it just happened that the compiler knows that, okay, if we store it back, it's not gonna get used, so I'm gonna delete that instruction. This is what the compiler helped in terms of like, it would go through the code and eliminate everything that's not needed. So your question is valid. Should we restore that value? Yeah. Does it add anything? No. So the compiler would ended up getting rid of that line. In fact, you in theory you don't if you know this is the only thing you do with this particular program, you don't even need this line, right? This line can be gone too. It depends on how the compiler optimizes it. This is a snippet of code that we got from compiling the program. So it is being slightly optimized, is how I should put it. All right, so if you let's kind of go back to the high level overview and conclude what are these stack-based languages where you compile the code and you get the assembly code that is in that follow the convention that we discussed earlier, right? Uh, these are basically any language that has recursion. C, Java, I think Python also has recursion supported, so that's also fine. Uh, code must be reentrant. Basically, multiple calls of the function can go back to the parent. I'll show you a picture again. What do I mean by that? It should be more clear when the picture show up. Uh, then we need to place some temporary variable to make sure that we pass everything correctly. So the arguments, right, should be placed in certain register. You need to manage the stack by correctly putting the return pointer on the stack correctly. And then if the local variable will overwrite some value, you need to make sure you save it before you call the function, right? Then the next thing is you need to then manage the stack to make sure this is ensure correctness. What do I mean? Basically, make sure you pop correctly. If you use a stack for intermediate inputs, be aware that is on the stack. The last thing I want to say is these are allocated in frame. is called stack frame. Basically, every time you have procedure calls, function calls, they have their own frame. And here's what do I mean by frame. What is this code? This code basically consists of the the outermost function u would call who, right? Who would then call mi twice, right? And mi would call itself one more time, right? So this is the call chain right here. Start with u, who, which then call mi, right? Twice. And each instance of mi would call mi again, because mi is recursive. Okay, that's a great question. So basically, the question is when we call multiply by 2 earlier. So let me go back to this code. Right? When we called this multiply by 2 earlier, we didn't save x and y. Why is that the case? In theory, if you want to make sure everything is safe, you need to do that. Actually, that's a great question, because in theory, you're supposed to do it. What happened is when you compile your program, the compiler realized that, okay, you don't have to do saving x and y because you have enough register that you are not going to overwrite x and y, and that's safe. Basically, you get the correct result anyway, so the compiler ended up not doing that for you. Think of it as the optimization. In theory, you're supposed to do it. But even if you're not doing that, you'll get the correct result, and that's fine. All right. Any questions? Okay, so let's come back to this stack chain, right? This stack chain. Here is basically what happened. Basically, the content of your stack, the content of your stack would have obviously the return information, right? This has happened when you do calq. You have the return information. And then this is basically the additional storage that you need inside a function, right? So what do you need to do? Essentially, you need to set up code. Like you need a setup code, right? Over here to actually save all the temporary register that might get overwritten over. And then when you finish the function call, make sure you revert the change, restore all this temp register. And that's why I said that was a great question about why you not saving x and y in that multiply function. You're supposed to. Basically, this is the proper management. It just happened that the compiler detects that, okay, you don't need to do that. And still you get correct results. So let me not do it. And here is the example, right? From the same call chain, you have the stack pointer, right? RBP is a different than RSP. RSP, we covered that already, right? It's a stack pointer. It points to the top location. Anyone want to guess what RBP is doing? Yep, point to the bottom of the stack. Why is that useful? So inside this, you have a bunch of temporary data. Yeah, it's almost the address to return to, but it's more like the old RSP that you can go back to when the function ends. So basically, at the end of the function, you know that you can go back to here, right? Back to here, and then you get the correct value of the stack pointer. It's a convenient way that you can manage the function call, right? Otherwise, you need to manually compute, like, okay, does my RSP go back by, I don't know, 12, 34, 15, whatever, right? Over here, you have this register that say, okay, when this function call done, come back here. Does it work like a triple pointer? Kind of. I mean, basically RBP is just the old value of RSP that it should come back to when you finish the function call. Think of it that way. I think it basically would make this a lot simpler. Why is that the case? Right now we are at the function called U, right? What happened here? We have to call the function called who, right? Basically who. What happened when you call this function is RSP would have this setup code and blah, blah, blah. You need to save the return value. Then you need to increment RSP. So this is what happened. You increment RSP. When you increment RSP, you then update RBP. You update RBP. Somehow old RBP would be stored here as well, right? So you can revert back once this function is done, but this is updated. So in this particular function, in this function called who, you know exactly when you're done, this is where you go back to. But before you finish it, you need to call another, basically two more functions, mi and mi, right? So the first mi would have update RSP and RBP as well, followed by the second mi, right? Which then call itself, let's say it's a recursion. And when you're done here, what happened is RSP would go back to here, right? So that at the end of the day, you have RSP and then RBP would be restored because you have the old RBP here. Oops, my bad. Old RBP. So that when you return from this function, you know how to return back, and you can return back again, you can return back again, you can return back and call another function and be done, right? This is essentially how deep can a stack get? Basically as much as you can, depending on the size of the DRAM. Depending on the size of your DRAM, it can keep going. I mean, you might have noticed, right? A lot of functions you call we need to do recursion, like Fibonacci, for example. If you call Fibonacci of, say, 30, how big is that? At minimum, you go 30 level deep, right? Because it's f of n minus 1 plus f of n minus 2. And that f of n minus 1 branch go down really far. So the stack can go up quite a lot. How much room do we have? I mean, how big is your memory? Yes, stack overflow can happen. So basically, your one of your friends comment that recursion might not be great because you can run into stack overflow. That's actually one of the reasons why recursion is not great. Because you keep using the memory. Has someone guessed what's the second reason on why calling a lot of function is not a good idea? Where is the stack? In DRAM, right? Yep, more load time. You need to keep accessing DRAM, and that's bad. So, so in C, when you call a function, you can actually add this keyword called inline. What inline function would do is instead of calling this, like use the stack, they would replace the code as if you copy and paste it inline. So is there a better optimization to recursion? If you take an OPL class or something like functional programming class, you can then realize there's another form of recursion called the tail recursion, which can always be converted into a loop. Basically, a loop would be a little bit better because you don't go to the you don't create, you don't expand the stack, right? You just loop around. So that's another better form of recursion. If you can convert to a tail recursion, then the compiler can optimize it. So hopefully for a few of you who took OPL before this class, hopefully that might clear up a little bit about the class I taught last semester when I said tail recursion is better. Exactly one of the reasons is because of this. It managed the memory access a little bit more efficiently. So here's the general overview. You have a stack frame, as I said earlier, right? And you notice here, basically you save the ORBP. Return address is stored here, arguments here. This is basically all the temp that you need inside the stack. And then these four things repeat down here, basically when you have a function call. And you keep doing the same thing, same management again and again and again and again, whenever you have a function call. So let's go through the example. This is the last set of example. I know it's a lot of slide number. It's not at the end yet, but bear with me. This is only one single example. I want to do increment by this value, right? So basically I have a function called increment. I want to add x, which is whatever my pointer is pointing to, by value and return that value. Return this. Oops, my bad. Okay, any questions about the C code? So, where's P? This is P, right? We return X, so we can move that to X. Add X to val. Where's val? Val is RSI, right? And then you do move Q RSI to P. The result of this, basically this line corresponds to this. Move Q RSI RDI. Right. Any questions about this translation from C to assembly? Okay, so we will use this function in the example. Basically, let's say we have a parent function that call this function, and let's say this call incr. This is the same old function from the earlier slide, right? And this is my input. This is star p. This is val. Any questions about the C code? Because we will then go to the example on the assembly. So let's go through this. This is the initial, right? The top part of whatever goes here is the initial stack structure, which I only have RSP, the return address. What do I do here? Why do I have to do this? So what is 15213? That's P, right? That's P. So we are saving P, right, to this. We're just saving V1. Basically, this is save V1. P and V1 are the same. Basically, that's whatever goes in, right? We want to save v1 to make sure that, hey, whatever value here can come back to v1. Why do we need this? Basically, it's kind of, think of it as almost like a malloc, but it's malloc on your stack. You are trying to save, like, hey, we want two slots on my stack to save the things here. Basically, we want two slots on the stack to save whatever I need to save here before I call my function. This is called setup code. Basically, I want to set up everything to make sure when I return from the function call, I have everything there and correct. Basically, in this code, it says I need two slots. The first slot is for v1. Right? The first slot is for v1. So this is the updated stack structure, right? You will then see this move out instead of move q, right? Not much different. Basically, move out is for 4 bytes instruction because 3000 is still within the 32 bits. So we can use move out instead of move q. It doesn't matter much. This is compiler optimization because move out take a little bit less space than move q. But at the end of the day, same story. That's the first node, right? Nothing much except for, well, 3000 is less than 4 bytes for sure. So you can use 4 bytes to store 3000. So let's just use move out. You notice LEAQ, right? LEAQ here. LEAQ is just an optimization on you are storing RDI, right? RDI with RSP plus 8. What is RSP plus 8? So there are two things you want to notice. What is RDI and what is RSP plus 8? I'm gonna get rid of these two boxes so you can see what are the two numbers. RSP plus 8 is 15 Right, so this is RDI just happen to be address of v1, right? Address of v1. This is address of whatever store this value. What is the variable that store 15 Okay, let me answer this before I go back to your question. One of the question right now is what is $ESI? Basically, that's ESI is for. Basically, ESI is like basically you take RSI, which is 8 bytes, and you take the only 4 bytes at the end. The least significant 4 bytes. That's ESI. All right. So basically here, V1 store 15 right? V1 store 15 So you would then notice that, hey, the value here you store on a stack, which is now RSI, RDI would then take in the address of V1, right? And what happened when I call this function? I basically increment, right? Increment 15213 by 3000, right? This is what happened. Basically, when I increment V1 by 3000, you get the updated value here. Updated V1, right? Because you already push in the address of V1 inside the increment function. If you go back to the C code, we just update the pointer. The value of the pointer, which is now in RSP plus 8, is updated. It's updated. Okay. LEAQ basically compute the address. So if you go back to the first series of this assembly lecture, you then notice that LEAQ, what it does is it computes whatever is this as an address, and then store result in the destination. Over here, what is my address? Base is RSP, right? Whatever is going into RSP is my base. Then you add 8. You add 8 to RSP, store to RDI. So RDI would be address of V1. Basically, it compute the address for you. So when you finish, right? When you finish this, when you call increment, basically what it does is it increment V1. So this is where V1 is, right? So it V1 got increment by 3000, right? Then what you need to do next is finish up code, because you are at the end of your function, right? At the end of your function here. You want to add V1 and V2 together, right? What is V1? This address is V1, right? What is that address? That address is RSP plus 8. Yeah, basically the value of V1 is 18213. The address of V1 is RSP plus 8. So you basically add RSP plus 8. What is V2? When you finish calling this, what is V2? V2 is the result of increment, right? Yes, it should be in RAX. So basically, this is essentially V1 plus V2, right? Then this value is now will overwrite RAX, right? And this is a return value, so you don't have to do anything else except because you allocate 2 slots, right, for this function. You need to deallocate that. So you add 16 to RSP to make sure everything come back, right, here, and return. And that's it. The reason why I skipped those 2 steps is because I already draw it on the PowerPoint slide earlier. Basically, you add V1 and V2 at this step, right? This step basically recover the RSP that you allocate before, go back to the earlier point, and then you return. That's basically the summary of the how you would call a function. If you still have more questions, I think the in-class exercise would be that we're going to have right now. It's going to be a good way to basically that you can kind of like go through another example on your own, and I'll be there to check and make sure you can follow everything. This is basically a summary again, the same slides here. Important point is when you have function calls, you use a stack because it grows from the same direction, and when you pop it back, you go back to the same point. Recursion is handled based on this convention, and there's no. Basically, pointers are basically address of values that we used earlier. For example, with the 15213 that get incremented by 3000 into 18213, right? So that's how you can play with the stack, play with register, play with inputs to the function, and play with the return address. And that's it for this lecture. Before we go to the in-class exercise, I want to kind of give a brief overview of what's coming next. We will talk about the rest of the material of this class. You can think of this as module 4, but it's a part of computer system. Basically, we'll talk about the memory, the DRAM, and how to make DRAM faster through caching. How many of you heard of the word cache before when you buy a processor? Like L1 cache, L2 cache. Hopefully, whenever next lecture come in, you have a little bit more idea of what they are and why they are really good at making DRAM faster. So we will talk about how to make data access fast, right? And I can assure you, this is one of the major bottleneck in every single program. And we'll talk about how the learn it from Comarc. Yeah, so basically, yeah, if you go and take ComArc, we'll cover this in way more detail. It's kind of like talk about how computer operates and how to make things fast. We also talk about how OS can prevent illegal accesses. If you're working on assignment 2, you probably hit that word already, segmentation fault. So parallel algorithm has a lot to do with memory management and caching because when you have parallel accesses, there's certain things you can do when you write a program to make it faster, and some of them has to do with caching. Oh yeah, it's related. Some theoretical complexity can come to life, and the main reason is actually because of memory. Sometimes the algorithm will say, hey, this O of n is perfect, right? But somehow your O of n has to access the memory every single time. That means that your O of n algorithm takes a long time to finish, right? Like merge sort. If you have to do a merge sort on a large element. Oh yeah. So that's a little bit different. So parallel merge sort has a lot to do with the fact that the original merge sort is not friendly toward multi-threading because there are a lot of dependency. Dependency means that I need to compute certain data before the next one. There are series of operations I have to do before the next piece of thing, which means that I can't parallelize them. I can't do them in parallel. Even though I buy a fancy processor with 30 cores, I will ended up using one CPU core because I need to finish this step before the next step. We will talk about virtual memory and why do they give the benefit that you see, and I was hoping that this part of the lecture I can kind of exploit the fact that I'm one of the expert in the world on this particular topic. So I'll try to make sure first of all it's easy to understand. I'll make sure it's fundamental. I'll make sure that it's a lot less memorization, but it's a lot more like understand how it works so that you don't have to memorize everything. And also hopefully this motivate you a little bit more either toward like, okay, maybe computer system is not as boring as you thought, or hardware is not as boring as you thought, or if you think it's still boring, okay, so some of you said it's still hard now. I mean, if you think it's hard and do like all this thing, hopefully when you write a program you are aware of there are things that can happen and make programs slow. But yeah, as I said, if you feel like anything is hard, let me know. I can schedule additional slots. Like the 2 hours per lecture kind of thing, it doesn't always support like like answering all your questions. I totally understand that. I'm trying to basically see how can I get you to actually understand certain concept better. So if you have specific questions, either on Discord, office hours, or additional meeting, that's fine. Just let me know. Okay, so before we leave today, you can go to in-class exercise 8. That's the end of the lecture today. I'll move to Discord because in class exercise 8 is more like a worksheet that you need to work on. It involves writing assembly code, but it's not long. So don't be too scared. It's not that long. It might be confusing, so that's why I'm gonna go to Discord channel both today, later today at 7 p.m. and Wednesday at 7 p.m. Right? So use those time, and if you still need more time, I'll try my best to basically schedule more of this. I don't know, like Discord, a live discussion. All right, so let me save the recording here real quick and switch back to my desktop.